Hello everyone, today we'll talk about the problem build a matrix with conditions. We're interested in numbers from 1 to k. We want to create a k by k square matrix such that all the cells are 0 except for k cells which contain each of the numbers from 1 to k exactly once. We can return any matrix that satisfies the conditions that were given, and the conditions are two lists, and every list, one is for rows, one is for columns, tells us that the row where one number is must be strictly smaller than the row where the second number is. So for instance, we can be told that we want to create a 3 by 3 matrix. So we have to put numbers 1, 2, 3 within it, the rest are zeros. And we know that 1 has to be above 2 in the matrix, 3 has to be to the right of 1, and so on. So we can express above, below, and to the left, to the right, and you want to return any matrix that satisfies all the conditions, or an empty matrix if those conditions are not satisfiable. Maybe it's already clear to you what to do, and if it isn't, then of course typically the first step when you wonder about a problem, and that problem is a 2D problem, you can think about what would happen if it was a one-dimensional problem. Because in some cases you have to drop some important sources of complexity, in which case you can solve this easier version, and maybe then the problem is to actually go from 1D to 2D. In other cases, such as this one, there are no interdependent, or there are not really interdependencies between 1D and 2D cases, because we can think about those rows and columns as essentially independent. What do I mean? First of all, in one-dimensional case, we just have to put the numbers on the line such that, as we're told that some numbers have to be to the left and to the right, then that it's possible, and that those k numbers are just placed on the line. And this is a very standard problem. It's called the topological sort problem, and indeed we'll be using a topological sort here. And the only difference is that, of course, our matrix is 2D, but we essentially have to topologically sort our values, so put them on the line from left to right based on column conditions, from up to down based on row conditions. If any of those are impossible, then it's impossible to build a matrix. It should be quite obvious. Otherwise, we can just independently determine the row and column for every value based on the appropriate topological sorting. And that is indeed what we're going to do in this case. So the heart of the solution would be a method to topologically sort a directed acyclic graph, or a directed graph at first. We have a list of edges. We want to number them from 0 for ease of use. And this is my favorite way of writing a topological sort. We create a graph. We keep also in mind the in degree of every vertex, so the number of edges that come into this vertex. And since a topological sort means that we can always start with the vertex that no edge comes into, and such a vertex must exist at the beginning, otherwise we have a cycle, because of course an empty matrix is returned exactly when we have a cycle in one of those list of conditions, at least one. So we keep the in degree in mind, we calculate the whole graph so that we know what are the edges pointing from any given node, what other nodes are pointed to, we count the incoming degree for every node, and now we'll be creating our topological sort step by step. At first we can put in any order all the vertices that do not have an in degree, so whose in degree is equal to 0, and for every vertex that we look at in our topological sort, we essentially remove all the edges from the graph. So for every neighbor in the graph, we reduce the incoming degree of that neighbor, and if that incoming degree is now 0, this is another node that we can add to our topological sort safely. We have topologically sorted our graph exactly when all the nodes at the end are in our list res. Of course, if you're not that familiar with Python, this is safe to iterate through a list that we're modifying like this. We'll be running after the end of the list will be running away from us, and at the end we want to end up with exactly k numbers in our list. And when we have those numbers, then we have to remember so now we know for every position, so for every essentially row, what value is in that row. We want for every value to know which row it's in, so we just have to essentially turn this table around. And instead of remembering for row or for column which value, we want to remember for every value which position. So for instance, which row or which column. And that is what we return after the topological sort. And the rest is very simple. We perform this topological sort on rows and on columns. And here we can check if we should return an empty matrix. Otherwise, we know for every value which row and which column to put it in. And indeed we'll be putting each value in a different row and in a different column, because why not? So we create the result, and for every value and its row and column, we put it in the matrix and return the final matrix.